All right, so to carry out an hypothesis test, the first thing we need to do is set up two contradictory hypotheses. One is called the null hypothesis, which is essentially the hypothesis for random chance. The other is the alternative hypothesis, which is that there's some kind of effect beyond random chance. After we have our hypotheses, then we collect the sample data. From there, we would determine the correct test and check the conditions, noting any assumptions that were made. Right now, we've only dealt with one type of test, and that's the randomization, and simulation test. But we'll have other ones coming up. From there, we would analyze the sample data by performing whatever calculations that ultimately will support one of those two hypotheses. And depending on how the sample data, how those calculations go, we will make a decision and write a meaningful conclusion. All right. So when it comes to hypotheses, again, we start off with two claims. One is called the null hypothesis, which is abbreviated H0, H naught. That's the claim that a population parameter has a certain value. And as this test goes, we start off assuming that this value is true. The general way to write it is H naught is equal to whatever the parameter is equal to some null value. Now the parameter is the value that we want to learn about. For us, it'll either be a proportion, a difference of two proportions, and later on a mean or difference of means. And the null value is just whatever we're trying to claim that it's equal to. The alternative hypothesis, which we abbreviate HA, that's the research hypothesis. It is usually a statement about the value of the parameter that we hope to prove. And generally speaking, the alternative will be written in the form of whatever that parameter is not equal to the null value. So for our class, hypotheses will be written in this format, where the null hypothesis is that the parameter is equal to some null value, and the alternative is that the parameter is not equal to some null value. Now, the alternative can technically also be written with less than or greater than. However, essentially starting with the next lesson on, the not equal to is going to be the better choice. If the evidence happens to point to the alternative being true, then and only then will we determine whether it's less or greater. But until we prove the alternative true first, we'll go with not equal to. Right. Once our hypothesis is written, the next steps are to collect and summarize the sample data. Specifically, what we're trying to find is compute the point estimate. And this is the sample value that estimates the parameter of the hypotheses. This is going to be the number that we compare to the null value. So if you're testing proportions, then the point estimate is going to be a sample proportion. If you're testing differences in proportions between two groups, then the point estimate is the differences in the sample proportions between the two groups. And so on. Whatever your parameter is, the point estimate is the sample equivalent. Okay. So once we have our hypotheses and our point estimate, then the next thing to do is look to see what random chance looks like under these conditions. And once we have that, then we go to see how our point estimate fits in. So this middle of this graph, you have this graph, the middle of it is always going to be the null value. That's going to be the center of the null distribution. And then somewhere along that horizontal axis is going to be the point estimate. The point estimate could be the left or could be the right. Either way. And then the amount that's above and farther away from the center is going to be what we know. That proportion is known as the p-value. So the p-value is the proportion of the null distribution that is above the point estimate or farther away from the null value. As a rule of thumb, for those cases where the null hypothesis is actually true, we do not want to incorrectly reject the null hypothesis more than 5% of the time. So this corresponds to what we call a significance level of 0.05. And the rule will follow is that if the p-value is smaller than this significance level, then we say the results are statistically significant. This means that the data provides such strong evidence against the null hypothesis that we'll reject it in favor of the alternative. That is, when the p-value is less than 0.05, we're going to find it more likely that the null hypothesis is true and less likely for the alternative. Let's try that again. If the p-value is smaller than 0.05, we would reject the null hypothesis. So we'll say the null hypothesis is not likely, and we'll go with the alternative. So essentially, random chance is not a likely explanation of the results from our sample. So if the p-value is less than 0.05, then we'll consider that to be statistically significant. That means that random chance is not the likely explanation, and we will reject the null hypothesis. If the p-value is not less than 0.05, so if it's more than 0.05, then it's not statistically significant, and we'll fail to reject the null hypothesis. Just as a general rule, we either reject or not reject the null hypothesis. We will never say we accept it, because the null hypothesis can never actually be proven to be true. For instance, the sample could just be too small to get meaningful results. So when we fail to reject the null hypothesis, the best we can say is that the null hypothesis is plausible for the parameter, but it's never going to be the only plausible value. And if you're wondering why we're using 0.05, well, that's a good question. Maybe we should use a bigger number, or maybe a smaller number. And if you're a little puzzled, hopefully that means you're reading this with a critical eye, so good job. The truth is 0.05 comes out to be 1 out of 20. 1/20th is 0.05, 5%. This is sort of a universally accepted cutoff point that dates to the early 20th century, to the statistics pioneer R.A. Fisher. Again, corresponds to 1 in 20, and essentially we consider that the border between plausible and not plausible, so between the likely and the unlikely. It is a bit arbitrary, and we'll may play around with it a little bit later. Right now, 0.05 just works very nicely, and especially with what we later call the normal, what we'll later see with the normal distribution.